Well, hello everybody, and thanks for joining me again for Shop Talk. It's fun putting these together, so I hope you enjoy them and have fun, and let me know what we can do to help you out with any other topics or anything Caleffi related. So a lot to cover again tonight. I'm going to roll through it pretty quickly. I do have a short video at the end. It's about 3 minutes, so after I do the slides, I'm going to switch presenters here because I got that on a different computer. Going to do the the video, and then I'll come back and we'll do some questions. And yeah, if you want to raise your hand through this, we can do questions. Kevin or Mary will shout out some questions, and keep an eye on whatever you type in. I almost had to make sure I show you my t-shirt there about electricity. I need a hydronic one like that, so if you can think of something, we'll get some of those printed up. So a little bit of housekeeping here. You know, if for some reason I'm not sounding real clear, that things are a little jerky or something, sometimes if you just log out and log back in, you might get a little better connection and it might sort that out. But there's just some GoToWebinar information if you really want to call and scream at them for something. So yeah, and thanks for the Mechanical Hub team for making all this possible. It was John and the boys over at Mechanical Hub that thought of this format, doing these things you know, after dinner, so to speak, I guess, or after dinner for some of you folks, I know. So we'll do the particle and magnetic separation today, and then I've got some really interesting primary secondary stuff I want to show you in the next one, which will of course include hydraulic separators and stuff like that. And then episode 4, I want to talk about how we transfer heat with different type of heat emitters and some kind of fun things there. So we'll roll into this one. Tonight we're going to do a donation. So at the end of it, there'll be like a post-webinar, a little response form that'll pop up on your screen as soon as we're done talking. And if you check in there that you want to donate, we're going to match donations up to $500 to the Red Cross for this. We're going to try and do this on every presentation, pick a charity, and you know, everybody's looking for help out there. And certainly if you can give blood, I'd encourage you to do that. So the Red Cross it'll be, and if you check that you're going to donate, then we'll match those funds up to 500. So thanks for that. All right, dirty deeds done dirt cheap. Who was that? ACDC? Or, yeah, should do a contest on that. So that's what we're going to talk about, is how we get dirt. I think of the two things that are the most common issues, problems, challenges with hydronic systems is air, number one, and dirt. I would say they're probably close to one another as far as that causes the most amount of problems with boilers, with pumps, with tubing, with everything we make. You know, when we have problems with it, it's usually related to crap in the water that's getting into our valves and our mechanisms and plugging them up. So I'll show you what we've been doing to deal with that, and some of the new products that we have that work a little bit better for that. So we're going to talk about big chunks, little chunks, magnetic chunks, and then you know, the procedures to implement that to make sure you get a good clean system. I wanted to, a couple things I talked about last week, I want to make sure I clear up a couple things that I said. Now, one of the things that's going to come into play here a lot as we talk about things is the velocity of the fluid going through the system, the speed of the water, basically miles per hour. Think of it that way. We talk about velocity of fluid is in feet per second. And when we start sizing pipe, I found if you go to this website, engineering toolbox, I think.com, they have all sorts of calculators like this one right down here, because I know there's some rules of thumb, like how much flow can you put in a 1-inch pipe, or, you know, 1.25 inch pipe, is steel pipe, is it copper pipe, is it PEX tubing? So, you know, I think you find if you go to these calculators that are made specifically for that tubing, you'll find out you can get some pretty good flow rates. Like right down here, I mean, I've heard for years that, oh, maybe 12 gallons a minute is about best you can do on 1.25 inch copper. Well, actually, if you look at type M 1.25 inch copper, you can see I can get up to about 18 feet per second, about 17 feet per second, and still be at that 4 feet per second velocity, 18 gallons per minute, excuse me, and still be around that, you know, 4 feet per second velocity. So where you can get a little bit balled up on this, if you look at PEX over here, because the inside diameter is quite a bit smaller because of the wall thickness, even though the outside is still copper tube size, you can see what happens over here with 1.25 inch PEX. So don't use a rule of thumb and say, if I use 1.25 inch tube, I can get, you know, X amount of gallons, 15 gallons a minute, whatever it might be. You know, these calculators are online. This is the one from the PPI, I guess, Plastic Pipe Institute. You can see up here, you can choose different types of tubing, different wall thicknesses, and then put it in there, and it gives you all this information. And this is going to be important too when we talk about flow velocity, whether you get turbulent or laminar flow conditions go through a pipe. I got some examples of that coming up, because that has to do with how we transfer heat, and also has to do with how we get air and dirt out of solution if the water's going too slow or too fast. Going too slow, it doesn't move the dirt with it. Going too fast, it just blows it right past your devices that are intended to pull it out. So we'll look at that, excuse me, a little bit more. And the other thing, I got a little heat on this last week when I talked about, you know, these scoop type of air purges. I said, yeah, I didn't think there was a place for them in today's hydronic system. Well, there kind of is. You know, if you're doing cast iron boilers, this type of air elimination device works. It doesn't get these little micro bubbles out. And to me, it's kind of like a rotary phone. Or would you buy a new pickup truck and say, hey, you know, I'd rather have a carburetor than fuel injection. I'm just used to that. I know how they work and this and that. Probably not. You know, you want the best performance. So definitely, if you're using high performance boilers, high efficiency boilers, I would go with a micro bubble type of thing, because I don't want these little micro bubbles in there anywhere. So I just wanted to clear it up that I'm not an air purger hater. I just think there's a better technology. I understand there's a big price difference between those two, but I think, you know, high performance systems require high performance air elimination. Dirt elimination is what we're going to get into next. And it turns out it's really about the same concept, the way we get air out and the way we get dirt out, when you see how we talk about separators instead of strainers or filters. So, and here's the other thing, I'll say one last thing about these air purges. There's another thing that we talked about, is you want to have a little bit of upstream piping if you're going to use this type of air purger. And I've heard it said a couple times that people say, well, you want to do that so you have laminar flow here. And no, you don't. The only way you get laminar flow here is you slow the velocity down that pipe. An 1.25 inch pipe, you've got to be down about a 1/2 gallon a minute flow rate before it turns laminar. So you're not getting laminar flow just by putting a straight section of pipe in there. What you are getting is the ability for these little bubbles to start rising up, and the buoyancy of the bubble in the water goes to the top. So when it gets in to this big wide chamber here, you already got a head start on getting those bubbles up to the top so they can get to the top and come out of the air eliminator. So you want to have that 18 to 24 inches upstream, and the reason you want to have that is so the bubbles start to rise to the top of the pipe. It's not slowing the velocity down there by having a straight section of pipe. So just be clear on that. And this is what we're looking at over here when we talk about laminar flow, transitional flow, and also turbulent flow. And if you're flowing between 2 and 4 feet per second in any size pipe, you're going to have turbulent flow, which is what we want, obviously, to move the heat out of that. So yeah, and when we get to the demo, you're actually going to see that. You can see in my clear tubing, you can see how that water actually squirrels through there as it goes down through the piping, indicating you do have turbulent flow in the range that we're going to run at, which is about 4 feet per second. So just to get that off of my mind to make sure I didn't you know, upset people when I said I didn't think they worked very well. All right, so here's what we're up against. This is a friend of mine, Kevin, back in back east there, that does a lot of boiler change outs. And I said, Kevin, when you drain these boilers out, you know, send me some pictures of what you find in these systems when you drain out an old cast iron boiler. These are going to get replacement boilers. So obviously, just looking at those two pictures, you don't want to just take this boiler out and put a new boiler in and allow this type of stuff to go into your new boiler. That's going to plug up your passageways. It's going to coat out your heat exchange surfaces. So number one, we want to flush that out as best we can before we put the new system in there, the new boiler, the new components. But we want to make sure that we've got a device in there that keeps working after we leave there that day. So any little particles that come out of this, this is called hematite, which is rust, as you and I know it. This is called magnetite, which is actually a kind of a sludge. It's almost like we call it boiler ink, because you look at it, it looks like black water, but if you let it dry or put some on your fingers, it's actually got a little gritty feeling to it. So there are actually metal particles in there. That's what happens when ferrous metals break down. They turn into this black sludge that we call magnetite. So I want to make sure that I put a device in there to be able to grab that, because I don't want that in my system. I don't want that in my pumps. And I'll show you an example of that as we get going, what happens when you do have magnetite and you put an ECM type circulator that has a strong magnet in it. Guess what? And we've got a product, if you do want to flush systems, you need a lot of flow. You need a lot of horsepower. So this is a purge cart that we make. It's got a 1/2 horsepower pump. So you should be able to get, you know, 10, 12 gallons per minute out of this. And that's adequate to, you know, purge like an 1.25 inch pipe. That'll get your velocity up to where you can start scrubbing that junk I just showed you in the previous slide. Will flush out at that type of velocity. Now, if you do larger systems, you know, make a bigger one of these. I've seen guys use old swimming pool pumps where you can get, you know, 30, 40 gallon a minute out of a 1 horsepower, 1.5 horse pool pump. Now you can really get some good flow going through your system, because you need that flow, you need that velocity to move that dirt around. And I'll show you the number, that the magic number that makes dirt really come out of systems. So the black product that I showed you, it's metal products that are in your system. The cast iron pump volutes, the expansion tank, any steel nipples you might have used are breaking down. And we talked about this last week. They're breaking down because you're getting oxygen in that system. It takes oxygen and water for the metal to break down. Usually it presents itself like this in an expansion tank first. Being the thinnest metal in the system, that's usually the first place that you're going to notice a pinhole or rust. So that's what that black sludge is this tank's breaking down, and it's turning into a black goop in your system. So again, we talked about oxygen ingress last week, how it gets in through non-barrier tubing, how it can get in around packings on valves and stuff like that. So it does tie into the dirt and particle removal, because this is what it's going to happen. Now, I'm pretty sure that didn't leave the factory. Looks like a take vent there, looking like that. So whatever's caused this thing to plug up, and it's probably not going to do a lot of air removal in that condition, was something in the system caused this to happen. And number one, we want to prevent that. We want to find out why this had so much sludge in the system, and we want to stop it, whatever it takes. We've got to tighten up our system. But also, we want to make sure that we've got a separator in there, that if there is some of this going on for a period of time after we flush it out, we want to make sure that we pull it out of harm's way. We don't want to trap it in a pipe or a strainer where it can plug up our, our flow rate. Now our boiler is going to go into lockout. Our pumps are going to start screaming and protest because they're not getting enough flow to it. So, and we are going to do I don't think I've got it keyed up yet. We're going to do a session on water quality. And water quality will tell you a lot about why this happens in your systems, why you get that sludge, why you get that buildup, why you get this. Obviously, this has been leaking, but these minerals that you see on the outside of this are an indication of what's in that water that's in your boiler. So here, maybe you're lucky that this leak, and you can see that you've got all these minerals in your water, because you really don't want those inside your boiler, your pumps, your piping. So we're going to show you in another water quality webinar how to deal with that and make sure that's not going on the inside of the pipes. So probably the first place that you're going to look when you see a problem like this is that one of two things happen to this boiler. I don't know if you can see it in the picture, but there's actually water spraying, squirting up. There's some pinholes. It's actually a couple pinholes in this. And the first thing you're going to notice about this little Geonoma heat exchanger is, number one, it's been overheated. Just looking at it, you can see how some of these tubes are burned pretty black. Some of them are in pretty good shape up here. So one of two things has happened, that this boiler didn't get enough flow going through it to scrub the fire into the water instead of into the metal like you see here. And either you had some airlocks, maybe some of these loops never got purged out completely. Maybe there's enough flow just to keep this boiler going, but it was running too hot. Or there was some dirt and debris that got in there and started coating out those tubes, and now you weren't getting good heat transfer from the burner into the heat exchanger there. And I actually have a little demo of that. I don't know how well I can show you this on the camera. But the way that type of boiler works is you have a bunch of coils in there, and they go to a header. So you have 4 of them that go to a header, then you've got 4 more next to it, and then over and over. So that's why in this picture there, you can see some of the tubes are in better shape than others, and some are turned black, which makes me think some of these were plugged up either with air gaps at the top, or they had sediment build up in there, and that's what caused those to overheat. And of course, that metal being this thick, this is a cutaway of that boiler, not that exact one, but that similar brand of boiler. And you can see I've got cardboard thickness of material there between my fire, which is on the I had a burner here somewhere. My fire is right here against that metal. And so if I've got a little bit of insulation from scale buildup there, I don't have heat transfer. So this boiler is going to be very sensitive. These water tube type of boilers are going to be very sensitive to mineral buildup inside there. So we've got to do a better job of getting the dirt and particles out of our system than what we've been previously doing, perhaps. So,
hey, Bob, this is Kevin.
Yeah.
Got a question from Bill D'Agostino. He asked if you mentioned about air getting in through the PEX tubing. What about those plastic PEX fittings? Are they going to let some air into the system as well compared to the brass fittings?
Yeah, I think he's talking about like a PEX composite fitting.
Yeah, I think so.
That's an excellent question. I see Max is on here. I should open up his mic and maybe he could address that. He works for Rahal, but I wouldn't think so. I would think if they were using that for a hydronic application, that it would have a barrier that oxygen wouldn't get through. That's an excellent question. I'm going to find out myself, because that would be a concern if you got all barrier tubing, but now your fittings are allowing oxygen to migrate through the wall of it. And I did clear that up. I talked to one of the experts at PPI after my last session. I said, did I present that properly when I talked about how oxygen can get through the wall of a tubing even though air can't leak out or water can't leak out? He said, yeah, it in fact does migrate through the wall of tubing, driven by temperature also. So I'll find out a little bit more. Maybe Max will type in a response or call me here and let me know what the scoop is on those composite fittings that we're using for PEX. Now, excellent question, by the way. So again, here's an example of a boiler that was taken out of a job in Indiana, and it was going to be replaced by a similar boiler like this here. And obviously, this is going to cause a problem if you put it inside of this tube. So number one, you're going to have to purge all this. This was an old iron pipe, cast iron radiator building in Indiana there. And obviously, you're going to want to purge as much of that out before you put this new boiler in there. Otherwise, it's just going to plug these tubes up, and within weeks or months, you could have a failure on that boiler if this rust and scale that's coming out of the pipe, coming out of the radiators, is getting inside here. So a good power purge first, but also I want to put something to protect this boiler and these small tubes from any flaking that's going to go on after you leave. Because as we all know, cast iron radiators are going to flake off probably for the rest of their life. So we want to have something in there to protect your components from that. I like this picture here. A friend of mine out in Utah, I got this from. A couple things you can see in this picture. And this is a little bit more about water quality, but it's also going to kind of lead into the separator I'm going to talk about. So this is a boiler that failed, obviously, and obviously you can see what's going on here. But in some of these tubes, you can see some of these are about halfway blocked off here. That one's what, maybe a third. That one's a quarter. That one's about halfway blocked off. Some down here are blocked off. And so what's happened to this boiler, it's had hard water in it. And so as the fire comes on, the minerals, the hardness in that water is attracted to that hot metal surface. And that's why you always see the mineral buildup on this type of tube on the inner layer of it, because that's where the flame is. That's the hottest point. So obviously, if you start plugging these up and you're not getting enough flow, that's when you start getting, I don't know if you can see them in here, pinholes in this, this type of boiler. Another interesting thing about this, if you understand how a ModCon boiler works, is that all the water that comes back to this boiler, the return water, it comes into the rear section of the boiler first, and that's where it scrubs the heat off the flue gas that's going out there. That's where we get that secondary sort of heat recovery from a condensing type of boiler. And look what's interesting here. Notice the difference in the tubes back here compared to here. Because I'm not running the high temperature that I'm seeing from my burner against the wall of the tubing, I'm just really seeing the flue gas temperature, let's say maybe 180 degrees. If I'm running about 160, I might expect 180 degrees going out my flue pipe here. So as a result, I'm not seeing any minerals precipitating out and sticking. Yeah, they're rusty from dirty water, but they're not building up at this white scale that you see here because I don't have that high intensity flame against the wall of my metal. So again, we'll talk about that when we talk about the minerals in your water and what minerals cause that scale, and other ones can go right through the system. But there's certain minerals that precipitate out. Calcium, magnesium will precipitate out as you start putting fire to water, just like your tea kettle. So what we've been doing for years is a device called a Y-string. I've got an example one here, and it's a simple enough device. It's just a Y-shaped fitting like this right here, and we just put a mesh in there. And so what that mesh does is the flow comes through here, through this, it has to go through that mesh to get to the other side. So this basket will trap the materials that's in there, which is a good thing. That they work fine. And the limitation of this type of device is as the strainer starts to plug up, as you can imagine, now I've got more and more pressure drop going across that Y strainer. So if I've got a pump or a boiler or something downstream from that, eventually I'm going to start reducing flow. Now, when you buy a Y strainer, you can buy them with different types of mesh. This is typical on the ones you probably find just over the counter off the shelf. This is what's called a number 20 mesh. And what that number means, if you measured an inch of that and you counted the holes, it would have 20 holes per inch. That's what a number 20 or a 40 or a 60 or an 80 or a coarser mesh would obviously be a number 10. You get down to a certain size and they go to a perforated metal instead of a screen. And usually those will be rated by the diameter of the hole in it. So that would be as you can see, an 1/8 inch hole on this type of perforated metal instead of a strainer in there. I like to use a Y strainer as a point of use device. And by that, I mean, if I'm going to put like an air handler in, I'm going to put a balancing valve or zone valve on it. If you look at the opening in the side of this is one of our 127 balancing valves. It's a dynamic balancing valve. And the way this valve works, as the water comes around the outside of this cartridge, the inner part of this cartridge is always moving based on the delta P of the pump. So basically, you buy this as a 1 GPM balancing valve. It always stays at 1 GPM because that cartridge is sliding. And when the cartridge slides, see this little funky shaped window there? It kind of looks like a cocktail glass or something. you can see by the pen I've got next to it, that's a pretty small opening. So if we go back a couple slides to that boiler with all that rust and stuff that came out, what do you think would happen to this device if some of that rust started coming through to it? So we always want to protect balancing valves specifically, but zone valves, anything with a Y strainer upstream of it. And the other thing that we would do with a Y strainer is that ideally we'd have a strainer like this that has a couple of PT ports, pressure temperature ports, and then you could stick a gauge in that, and that would indicate when this strainer is starting to plug up or it's plugged up. If the pressure differential keeps going up and up and across that, obviously we're not getting flow through it. So that's why often when you see a nice quality a Y strainer like this that's being connected with some balancing components or control valves or something like that, you'll typically see them with a sample ports on that, so you can go up to them and just take a quick pressure test. And I don't know if you guys have ever used that, but it's just a simple pressure gauge, and it comes with a little needle on it like that, and you just wet that with your mouth and you stick it in through that little window in those little ports there, and now you can read the pressure across it. So if I read the pressure on both sides, you'll see the pressure differential, and that tells you that strainer is plugged up. So still a good application for these little Y strainers that, like I say, a point of use right at your final control valve, your mixing valve, your zone valve, whatever it might be. And sometimes when you buy coil kits for like air handlers, they'll come with all those components. They'll come with a control valve, they might come with a balancing valve, and they'll typically have a Y strainer with them to protect those different components. So yeah, that's what we call a pressure independent balancing valve, in that it moves by itself and balances the flow without you having to make an adjustment on it. So this is what we put in the systems. In addition, what's in that boiler when you get there, the boiler that Kevin took out of those previous pictures, this is what could be in there. I mean, if you're threading your pipe, you might get some of that in there. If you're using Teflon tape, especially, and if you go off the end of the nipple and you screw it together, you got Teflon tape inside your system. If you're welding, if you're grinding, if you're reaming with a pencil reamer, if you're cutting with a bandsaw, all that stuff's going to be in your system. So we want to, number one, flush it out the best we can when we start it, but we also want to have a device that's going to keep track of all that stuff as it goes around in our system for years and years to come. So getting back to the basket strainer, here's what it looks like. And this is why we would put a gauge on either side of that, or take one gauge and take a reading on both sides. That's an indication that we're plugging up like this. And now this, sometimes you can just blow them down here with a valve. Sometimes you actually have to disassemble and pull this little strainer right out and just take a toothbrush or something to it and clean it off, because yeah, when you get 70% of it plugged up like that, you're going to have a pump that's starving for flow, or you're going to have a boiler that's going in a high temperature lockout. So in fact, this was just on heating help, oddly enough. 2 days ago, this somebody wrote in there, oh, my indirect tank, I'm not getting very much performance. It takes hours for it to catch up. It never used to do that. And so he sends in a picture, and the first thing everybody that knows this sees is there's a Y strainer. And we said, have you ever checked that Y strainer in the, I don't know, 15 years or whatever this indirect tank has been in there? And he said, I've never had a problem before. Well, wouldn't hurt to check it. And certainly that's what he found when he took it out of there. That's on a piece of paper. So obviously that wasn't allowing a lot. I'm surprised he was getting any recovery out of that indirect tank with that much sludge built up inside that Y strainer. So the Y strainer had done its job. It's just nobody ever went back to service it and take it apart. So if you were to go and buy a brand new Y strainer tomorrow with, say, a number 20 mesh in it, and you put a flow test on that and took a pressure gauge like I just showed you, you would see a brand new Y strainer just out of the box. It's going to have about a pound and a half of pressure drop to it. And that's because of the mesh size of the strainer is just reducing the flow through it. Now, when that strainer gets plugged up like this, the one we just showed you previously, let's call that 70% of the mesh is plugged up. Look what happens to the pressure drop. Now think about that. If you've got a circulator that can only develop about 6 pounds of pressure drop, you got no flow going through that strainer. So somebody has to go and service that strainer. So there's probably a lot of Y strainers out there as we speak that need to be serviced. They might not be plugged up this bad, but the performance of everything in your system, your boiler, your pumps, your heat emitters, are all taking a hit because they can't get sufficient flow through them. So with that in mind, we came up with this idea. You said, you know what? Why wouldn't we put the same concept to use that we do in our air separator? And I think we talked about this last week. So there's an air separator, and inside this air separator is this coalescing media that we put in there. Can you see that okay? So what if we took that same philosophy of slowing the flow down as it comes in this, and what if we took this off the top of it and we flip this upside down and we put a dome on the bottom of it? Now we've got a dirt separator. In fact, I'm even going to put a magnet on the bottom of that, and now I'm going to do dirt separation with the media. In fact, the spider web in there. I'm going to do magnetic separation, and actually I could even put an air vent on the top of that if I wanted to. So this little device here, how it differs so much from a Y strainer is that as the debris, I'll just show you in this picture right here, as the debris comes in there, it collides. I call it a collision media. It's actually a coalescing media. The particles hit that and they fall down to the bottom and they collect down in this little dome at the bottom of it. So I don't obstruct my flow going through here because I don't have a screen, a fine mesh screen that's trapping all that stuff in the road, so to speak. I'm driving it off the road. I'm putting it in the ditch, I guess, by putting it down here instead of keeping it in the road, which is what I do with a Y strainer. So, you know, it didn't take a lot of magic. It just took somebody thinking, you know, we'll slow the fluid down because we're coming into a big chamber here. And if I slow the fluid down, some of the stuff's going to fall out just because I slowed it down to almost zero flow going through here. The rest of it, it's going to hit that little median there and it's going to drive it to the bottom. And these things, and you know, there's other brands. We're not the only company that does this, but probably after 50 passages, I'll show you some of the testing we do on this. You're going to have 90% of that particle pulled out of that. The big particles, you're going to get probably the first trip through there. The very small particles, I'm talking about the thickness of a hair, going to take a few trips around there for all that to be driven out of solution. But that's the key to a dirt separator as opposed to a dirt strainer, a Y strainer, a basket strainer, whatever you want to call it. And we make different ones. We make these up to 2-inch in a brass version. After that, it gets to be a lot of brass, so we go to a welded steel vessel here. So we've got these anywhere from 3/4 up to 14-inch pipe size. So if you've got an application where you want to try a separator, maybe you've got an older system that you've had a lot of problems with, let us know. And so here's an example of the range that we can cover on these separators. And what we do when we test these, we run them at a typical 4 feet per second. I mean, that's usually the high end of what's accepted in a hydronic system. We want to be between 2 and 4 feet per second, but we'll run these things out to 10 feet per second velocity, which way beyond what you would typically have, but it could happen. So we check the performance. We actually bench test these at these kind of flow rates to make sure that even if somebody does overpump one of these systems, that we're still going to get good particle removal out of that. And this one here, both of these are magnetic functions. This is the one I'm going to show you a little bit later on the display behind us with the magnetic band. This one has, looks like 3 magnets going up inside of it here that collect those fine particles when they go through there. So all of our magnetic separators started life as a dirt separator, and then we added the magnetic function. So we feel that we do a better job getting stuff out with our separator, and then the magnet is the bonus to get those little fine particles, because it seems if you look around, you'll see the race is on to put a bigger magnet in. Wow, I've got more magnets or bigger magnets than the Caleffi brand. Well, we don't need a big magnet because we're using that coalescing media, which actually swirls it a little bit in there. You'll see one right behind me here when we do that demo. The magnet is just getting the small particles that the coalescing media has a hard time getting anything below about a 5 micron. It's pretty tough to get out with the media. So that's where the magnet comes in. I'm going to show you why that's so important here in a couple slides. So now the other thing too, I meant to say this a little bit earlier when I talked about pipe size. When we do pipe sizing, we usually size the pipe by the velocity. We're trying to stay under 4 feet per second. That's up until you get to about 2-inch pipe size. 2-inch pipe size and larger, the engineers actually size it by pressure drop per 100 feet of pipe. So you tend to get a little bit higher velocity in the larger diameter pipe than you will in the smaller pipe where you're just using the velocity number, because they're using a different calculation on that. And I think it's an ASHRAE standard actually that tells you the acceptable velocity on larger diameter pipes based on the pressure drop, not on the flow velocity going through it. And it's usually about 2-inch pipe and larger that we'll get away from the velocity sizing.
Bob, can I interrupt you for a minute?
Yeah,
this is Mary.
please do.
We have a question from Flavio. Flavio, if you unmute yourself, you can actually ask Bob.
Yeah. Excuse me.
Whoops.
I got too much stuff on my swag here.
Okay.
Can you hear you?
Yeah, I wasn't able to unmute him, but
No.
okay, I'm sorry. Keep on then.
That's all right. Well, type it in, or we can try again later. Sometimes you have to, we've got to unmute you, and then you have to unmute on your end. It's kind of a two-step process, so we can open up and talk to you, but we can try again. So, or type it in, and Kevin or Mary will read it off too. So knowing that a lot of the new boilers are wall hung and the piping either comes out of the bottom or the top, we decided to come up with this device right here that can go on a vertical pipe. In fact, if you loosen this collar, you can make this a vertical or horizontal. So it's pretty nice that way, that you can get it into a nice tight spacing if you've got to get all your piping right under the boiler. So right now this is available in a 3/4 and 1 inch version of it. It's super easy, number one, to put in, and number two, if you shut off these two valves, you can actually blow it down here, and you can actually, this lid, you can open it up by hand. I'll show you the one on the back when we get going, and you can actually reach in there and pull the mesh out of there. And if you have to inspect that or clean it or replace it someday, it does have that same composite type of media in there, so it's not going to be affected by aggressive glycol. If your glycol pH goes off, some of the metal type of medias in there can start to disassemble and come apart. So we do use a composite body, composite media, brass housing and valves and stuff like that. Nice thing about that, if you keep this on your truck, you could use it for either application, turn it horizontal, turn it vertically by just loosening up the collar there. We've actually, let me go back for a second. We've actually got some really good, if you go to a Caleffi YouTube channel, you can see some really nice animated videos on how these different products work that they put together in Italy. And obviously this is a European look to, to a boiler installation, but it's a good place to go and see, how the particles and stuff work in a kind of an animated video. All right, so let's talk about particle size and the big difference between a Y strainer and a separator, a dirt separator. So this is it kind of just gives you an indication of what particle sizes, how they compare to one another. So probably everybody's familiar with coffee grounds and beach sand and table salt. So as you go around this here ring, you can see we get smaller and smaller and smaller. In fact, bacteria, we're getting down, probably, somewhere around the 2 micron. We can still pull that out with some of the cartridge filters out there. But when we get down into this range right here, it gets pretty hard to separate out of a system. Now, if that range happens to be a metal particle, I'm going to catch that with my magnet. But if you look over here, and these are actual tests that we've done in the lab over in Italy of different products. So you can see where the Y strainer is going to kind of limit it out at this particle size here. And the reason for that is the size of the mesh. Now I could put what I call a special filter, and I could put a really fine mesh in a Y strainer, maybe a number 60 or something like that. And I'm going to get down to a smaller particle size, but I will plug that up quicker too. So there's kind of a trade-off when you go with a finer and finer mesh. Now cartridge filter, this is more like like you might see on a water system, with the big blue cartridge that you can spin off there. You can get a little bit more surface area, a little bit more finer mesh, and still have some good capacity in that. So you can see we're going to go down to a little smaller range. But now if you look at the dirt cal, we're going all the way down to a 5 micron, which is going to be somewhere down in this range right here. As you can see, a spider web, we all know what that is. That's about a 2 to 3 micron particle. So a 5 micron is just a little bit larger than that. And the reason that this goes so much beyond the other ones is because I'm driving that stuff out of solution. I'm not trying to catch it and trap it and then clean it out. I'm driving it down to the bottom of that. And you'll see when we run this, I'm getting stuff that you can barely see with your eye. It's such a small particle. And now if I add a magnet to that, I'm going to go down below a 5 micron. In fact, I can get down to a 0.05 micron pulled out of a solution with a magnet. If it's a steel particle, it's going to stick to that magnet. And so if you look at the operating capability of this type of a dirt separator with the magnetic function added to it, now I'm down to a 0.05. You're never going to get that with a Y strainer. You're not going to get that with any other device. So we've got a device that works better down to a smaller particle size. It doesn't plug up because we're not trapping it in the screen. So this is why I'm trying to encourage people to start looking at separators instead of strainers, especially on high efficiency equipment where those small particles do matter on those tight heat exchangers. So what else did I have here? Oh, yeah, I think that covers it. All right, so what I did for the demo we're going to show you, I said, okay, let me just make some particles. So I did 3 things. Is I took my little portaband here and I cut a piece of, this is a piece of 400 grade of stainless, 409 stainless. The nice thing about if you use this for your demo, it doesn't rust in my tubing and turn my tubing red in there. So, but the thing about all 400 grades of stainless is they do stick to a magnet. As you can see, a magnet stuck right on the side of that piece of a stainless that I have. So I cut some of it with this. I used a chop saw and cut some of it because it gives me a bigger chunk. And then I actually took I got a little belt sander on the bench there with I think a 120 grit belt, and I sanded some of this so I could get just a tiny little speck of a particle. So I've got particles of I've got some copper that I'm going to show you. I've got some sawdust. I've chopped up some PVC pipe, all the things that you might find in the system as you put them together. And I made a little conglomeration of that, and I'm going to put it in the display behind you, and I'm going to run it, and I'm going to show you how this, how we can pull all that stuff out of solution here in a minute. Let me go. I got a couple
Bob,
more
we've got another question
All
from
right,
Benjamin Hicken. All
okay.
righty, I'm going to unmute you.
All
Okay,
right.
Benjamin.
Hi. Maybe.
Can you hear us, Benjamin? Okay.
No, I
Well,
don't hear him.
another false alarm. Sorry, Bob.
He did
No.
enter a question in the question field.
Okay.
All right. Well,
Says, Benjamin says, do steel dirt mags as opposed to brass work as well? Wouldn't steel construction interfere?
Yeah, and that's a great question because you say, well, isn't the whole thing turned into a big chunk of magnet? So what we do on the steel ones is this is actually a brass dry well that goes in here, and the magnet goes into that brass dry well. So the magnet isn't against the side of the metal, because yeah, you could turn that whole thing into a magnet. Then how do you get the stuff out of there? So what it does on the steel ones, if you unscrew this right here and you pull this out of the dry well, it's segmented so it can break, so you can get it out of there if it's close to the ground. And when you pull those magnets out, everything settles to the bottom of that, and then you just open the flush valve and it comes out. Now, Kevin, if you want to add anything to that, but that's the theory how the steel vessels can work with a magnetic separation function on them.
Oh, that's good.
All right, thanks. Glad you said that. All right, so what I want you to do from this day forward, when you take a circulator pump apart, and you know how you take the 4 Allen bolts off and you pull your motor off, and this is what you see is a little impeller in there, take your pocket knife or a screwdriver, your thumbnail, whatever you have with you that day, and just scrape that off a little bit. And if the particles that you scrape off of that stick to a magnet, like I'm showing in the drawing here, you've got magnetite in your system. And magnetite is what happens when any metal particle in your system, or any metal component in your system, breaks down to this black sludge, this boiler ink. It looks like black water, but you can imagine if I mix that in black water, it looks like an Etch-a-Sketch on there, but once it's in water, it just looks like black, dirty water, when in fact, it's metal particles. And this can be a problem if this pump is going to get changed out with one of the new ECM pumps, because these little particles, I'll show you what can happen to them if we've got a strong magnet somewhere in our circulator pump. So it's a simple thing to do. Just, you probably have a magnet on one of your screwdrivers already that you could use to do a test like that. So here is doesn't matter what brand it is. So this is what's called a wet rotor circulator. And the way a wet rotor circulator works is there's a hole through the center of the shaft, and that impeller at the end, the water goes through that, and the water that goes through that ends up inside there. And that's why this is called a wet rotor circulator, because this rotor is actually spinning in the water that's trapped inside. This is called the rotor can, and this is called the rotor. Now, when you take your pump off, your motor off of here, you kind of need to get like a screwdriver in there, a couple of them, and just wiggle, wiggle, wiggle to be able to pull that out. They come out a little hard because that bushing goes, that bearing goes into a bushing. I don't know, I can turn that one off to see it in there. So it does take a little bit to pull it out. So the way this type of circulator works is that's a really strong permanent magnet motor in there. And so if you have something like this, I don't know if I can tip enough, you can see it without dumping it on my computer, and you put it in there, guess what happens? Kind of looks like the bearded man on your Etch-a-Sketch. And so if those particles get pulled to that magnet's in there, and that magnet's trying to run inside there, you can imagine what happens is that's going to bind up that, get on my computer here, going to bind up that rotor inside there. So if you've got a circulator that's slowing down, all of a sudden you're not getting the flow, or maybe it even spits out an error code on its little digital readout. In fact, in the picture there was actually a pump that we took out of a system that was having issues, wasn't spinning, number one. But that's what happened is this little fine powder, iron ferrite, magnetite, was being pulled through the center of this and attracted to that magnet, and it was locked up in here. Now the pump manufacturers are stepping up, and they're trying to minimize this happening. They're putting barriers in there, they're putting special seals in there. This is actually a ceramic shaft, so it doesn't stick to the shaft here. But I'm of the opinion, as long as water can get through that shaft, through that hole, it can bring a particle that's the size of smoke, really. That's the micron size of particle that we could be looking at here. So I had one of the pump people tell me, well, you know, the water that goes into that rotor can, the very first day that you start that system up, it goes in there and stays in there. It doesn't leave and come back in and bring junk in and out with. I said, well, I believe that, and that's probably true. But I said, if the magnet's in there and there's a hole through the shaft, won't the little particles come through that hole and be attracted to the magnet? I mean, how else is this happening? I mean, that pump didn't get installed looking like that. Somehow that debris came through that shaft, regardless of the water leaving and coming to this here rotor can space, and pull those particles in there. So it's not something that we're making up. And here's the issue with that. This has been in our systems for generations, since whenever we've had iron boilers or steel pipe or anything that's made out of a ferrous metal. This has been going on in our systems. But what happens is, in a cast iron boiler, it just settles to the bottom of those sections and it lays in there and it doesn't bother anybody. Yeah, you lost a little bit of efficiency probably on that boiler, but it isn't causing harm to the system. Why it's important now is as soon as we went to this type of circulator with a strong permanent magnet, now we started having issues. And that's why this whole technology evolved, is these having to put magnetic separators in systems that we've never had to use before, because we didn't have, this becomes your magnetic separator. If you don't put something upstream of this, that's where you're going to find your magnetic particles, and it's not a good place to be trapping the particles. So, and I've got dozens of pictures like this. Is actually in our building in Milwaukee, and this is an expensive pump. This is like a $1,500 circulator. It's a larger pump, and we had one fail, and we called the manufacturer, and they said, oh yeah, send it back. It's just a software issue. We'll replace it, no problem. All right. And I happened to be up there the day that this happened. We come in, the building was cold. We weren't getting any heat. I go into the room and I see this one pump is flashing lights. I don't remember exactly what the error code was. I said, you know, that's odd that the second pump would fail in 2 years after the first one. I said, something else is going on here. I said, let me just, before we send it back, let's take it apart and see what's going on in here. So as you can see, I took the bolts out, I took the motor off, I took the rotor can off, and that's what I found. And I took a white paper towel and just wiped across that, and I had a palm full of this black powder that, again, it was like, it's almost like if you take a pencil and take your pocket knife and sharpen the pencil, that's the type of a particle size that we're talking about here. So it goes through the systems and it gets attracted to this magnet, and it's locked up the second circulator on the system. Now, my bigger concern is where is coming from, because I should be treating the problem, not the symptom. The symptom is my pump stopped spinning. The problem is, where is the magnetite being formed in the system, and it's coming in through the non-barrier tubing. The oxygen comes in, which keeps breaking down my metal parts. So this is this is our lab over in Italy. We've got a bunch of different rooms like this, and this is how we test different components. This looks like an air elimination test that we're doing here. So we'll pump air into the system, and then we can measure how much air comes out of it. We can measure how quickly it comes out. We can run this, as you can see by the pumps down here, at pretty high flow velocities there. See how this product performs when it's being over pumped and stuff like that. And we do the same thing for dirt, and we'll take our competitor's product over there and put it on a test bench and say, okay, how do they stack up against ours? I will say, when we talk about these type of air separators, I don't see a huge difference from brand to brand. You'll see feature differences in the Caleffi compared to some of the others, but the performance with that mesh or that media or that rings or whatever technology our competitors are using, they all do a good job of air removal, and I would think the same for dirt removal. I think we've got a little bit of an advantage on our dirt separators in that we started out as a dirt separator, not a magnetic separator. We had the magnetic function, so you really get a dual purpose a device or function out of it. So now this is going to take a little second, because what we have to do is I got to switch to my wife's computer because mine wouldn't play my quick player. And we're going to do about a 3-minute video of the display behind me here. And then I'll come back and we'll talk a little bit more about what you just saw. And then I'm going to, we'll do whatever questions we have. So Mary, can you make Ellen present? See if we can fire this up.
You bet.
All right. I'm going to turn off my mic so we don't have feedback here. Okay, webcams closed by organizer. Hi, Bob, Hot Rod Rohr. Ready for some shop talk? I am. So let me show you what I've got going on here. This is a clear plastic hydronic display that I built, and it shows, now let me talk about hydronics first. Hydronics could be a solar thermal system, it could be a geosystem, it could be a chilled water system, it could be a hot water system. Really anything that's a fluid-based water glycol heat transfer mechanism is what we're talking about in hydronics. So this one here is just going to be plain water, a little bit of color in it so you can see what's going on. Over here, this is kind of a clear plastic model of a Caleffi disco dirt mag. And by that, I mean I do air removal up here, which I'll show you in a second, and I've got dirt removal in the center, which comes out the bottom here. And I've also got a little magnetic band that gets very small particles, smaller than we could knock out with just the immediate side there. So what I'm going to do is I'm going to get this thing set up. I'll show you how it runs here. If you move over here, I've got some flow going through there. You can see I've got about 6 gallons a minute going through that. I'm going to go over to the side there, and I'm going to put some particles in. I'll show you what they are. And we're going to fire it up, and you're going to see that stuff come around, and you're going to see how the separator over here works for particle removal. Let's go. All right, so what I have here is a sheet of typical stuff you would find in a piping system. I've got some copper that I cut with a chop saw, so it's pretty coarse. I've got some copper here that I cut with a band saw, so it's pretty fine. And then some of this other stuff here is actually a 400 grade stainless, which is nice. It's magnetic, but it won't rust and turn all my piping red inside. So got some sand in there, good dirt, typical stuff. So we're going to gather all this up, and we're going to put it in that system, and we're going to fire it up, and you'll see how all this is going to come out in that separator, both the fine particles, the big particles, everything you see on this sheet. So that's phase 2. Let's get going. So we put a little debris in here. See it coming down here. Let's get our pump started up. And you can see it going around here. Now you'll see it coming out. Let's go over to the other side. It's going to take a minute or so, but you see how the stuff hits that little median side there, which drives it down. And this little magnet I just taped down so you can see it when I pull it off, a little bit better visual of all the stuff coming around through there. So everything I dumped in is now going to separate, and then I'll be able to blow it out here in a second. Actually, if I had an accurate scale, I could weigh what comes out. It'd be pretty close to what I put in there. Some of it's getting trapped, as you can see where I glued this together in there, but most of it's going to end up down here. So you can see some of the PVC chips and some of the wood chips, the lighter particles are starting to come out of solution there, and then you can see them all falling down here. So let's let this run for like a minute, and then we'll come back and we'll show you how this blows out, and we'll show you all the stuff that comes out of it. So what I've done is I've taken one of the magnets out of another collar, and I've just taped it onto that. It's going to be easier for you to see when I pull it off as trying to pull the whole band off. You can't see what's behind it. So let me show you what's going on now. You can see if I take this tape off, you can see all that stainless steel that I put in there. I actually move it around with the magnet. If I get the tape off here, give me a second. See how the magnet moves it around? Now what I'll do is I'll pull a magnet. It's going to fall to the bottom, and then I'll show you how we flush it out. So it goes to the bottom. The cup down here. Just open this up. Sometimes I run the pump to a little more pressure coming out of there. Well, you can see in there, but you can see how that particle that just dropped off the magnet, some of it's still in there. I got to flush it a little better, but typical hydronic system, you'd have a little pressure. This doesn't have any pressure on it to help blow it out, but it just gives you a good visual how these little magnets pull out those very tiny, small particles that you can get out with just a regular strainer, regular separator. So that's what I've got today. Thanks for watching. See you next time.
Open up your.
All right, I think I'm back. Can you folks hear me? Screen
Sure.
back over here.
Yeah, we can hear you. Just get your PowerPoint back up there and you're back in business.
All right. Can you hear me, Kevin?
I can hear you, Bob.
All right. Well, if there's any questions, now would be a good time. We can talk about that demo or anything. I saw there was some typed in when I went over and watched the video, but
Yeah, let me go through here and see what we've got. Nicholas says, I know it's frowned upon, but could the magnetic separator be used on a steam boiler with a hydronic loop for an indirect water heater to protect the hydronic side of the boiler?
I would say yes, as long as it's within the temperature range of our product, which, do you know that offhand on the brass one, Kevin, what the temperature range is on that? Is it 210 or 250? I'd have to look that up. Wasn't ready for that, unless you have it. But yeah, I mean, as long as the, the median there can handle the temperature. Now on our bigger ones, I will say any time you have a welded steel vessel, that does have a stainless steel median there, because obviously we can't weld against the composite median there. So if it's a larger than 2-inch pipe size and it's a steel vessel, yeah, for sure that could handle the temperature because it's steel and stainless steel, where the brass ones do have a composite in there. But we'll find out for sure with the temperature rating on that. But I would imagine it's well over
250.
200.
Yeah, they're good. They're good to 250. The brass dirt mags.
Okay, well, there you go. So, yeah, I mean, I don't know why not, Kevin, on the hydronic loop off a steam boiler, as long as our temperatures in that, I would imagine on the hydronic side, it's going to certainly below 250, even on the steam side, I would imagine, unless it's a high pressure steam application. Yep. So,
yeah, that's true. That's true.
Right.
Let me see, what else do we have? Any other questions?
Max.
Here we go. Steve asked, we were just introduced to dirt separators 2 years ago. How long have they been on the market?
Well, the dirt separators we've had around for a while. The magnetic was, and you know what's unique about Caleffi is that a lot of the things that we discover here happened over in Europe years before they got here. I saw ECM circulators at the issue in 1994, and I don't know when they started making over here, well into the 2000s. So some of the products that Caleffi developed, we developed for products that we learned were having issues over in Europe before they came over across the pond to the US market. And that's where we developed that magnetic separator function. We said, hey, these little circulators are having problems with the magnetic particles in our system. So some of those products we had developed, and then when the market was right over here, when we started seeing ECMs making their way into the market over here, and they started having those problems, just like we knew they would. So I don't know that. Do you remember what year when we first offered those? That might be before Kevin even started with Caleffi, when we started offering the. Well, we've had dirt separators forever, but the magnetic function to it specifically.
Maybe 8 or 9 years, maybe.
Yeah. Yeah, we saw that coming, and we had products ready to go. So here's what happens when we make a product for the world market, really. Everything else in the world is on the metric system. So everything we make for Europe is metric. So then when we need a product over here, we've got to, change it to NPT thread. We've got to get some listings on it and stuff like that. So it sometimes takes a few steps for us to be able to bring a product that we already have developed for the European market and bring it into the US market, because we have to do some upgrading and changing too. Sometimes we have to make a new forging if there isn't enough metal in that forging to machine an NPT thread in it, which has happened a couple times. So I would like to think we're kind of the pioneer on a lot of these products that you're seeing that are kind of unique, because again, we got the advantage of having an Italian parent company that's, probably seen some of this stuff before, like the ModCon boilers. Those were over in Europe before. I think probably I'd credit maybe Dave Davies at Heat Transfer Product for bringing the first one over here. Certainly taking a lot of arrows in the back for being that pioneer. But I mean, he found that product over in one of the shows over there. It came out of France, that little Genome heat exchanger I showed you earlier. So again, we knew some of the issues with that, and that's what kind of led us to developing the hydro separator, which we're going to get to in another webinar. We knew the hydro separator could fix all the problems that we're going to develop because of those high pressure drop heat exchanger type of boilers, the Genomes, other brands out there too, but that's probably the predominant one. So that's how we had product already developed for that before it hit the US market. So
we did get an answer from Max on the question about oxygen diffusion through polymer fittings. It's not a significant amount. He doesn't have an exact answer in terms of milligrams per square meter, but it's insignificant.
All right, there you have it. And again, oxygen diffusion, the higher the temperature, the higher the infusion. So, if you're running radiant temperatures, I would say it would be a non-issue. If you're running 120 degrees, you start running up around 180 for baseboard, then you'd have a little bit more potential for the oxygen to get in. I should probably put it that way.
Yeah, it's another good question from Stephen Jansen on the larger separators, 2-inch and up with the magnets. Can they be blown down with the pump running, or do we shut it down?
Well, the only thing is what you saw on my display, I didn't have any pressure on that because it's plastic tube and I can't pressurize it. So I didn't get a good blast on when I opened that valve. You saw that big chunk of metal particle that had been on the magnet came out right away. But if I would have had a little pressure on it, and that's why I tried to run the pump a little bit until it got out of fluid to try and get a little bit a better flush out of that. But the only thing about running the pump, if you blow that down, you better make sure you have a fill valve on there that can keep up with whatever you're going to blow down, because you could start to, get airlock in that pump if you're draining fluid out of a separator and you're not making up the water as fast and you're blowing it down. So I like running the pump, and that I get a little extra motion through there to kind of blow it out. But certainly you'd want to shut it off if you're worried about, getting an air bubble in there and locking up, especially on a big, expensive pump. You don't want to have a problem with that. So do you have an opinion on that, Kevin? It's better to shut the pump off or leaving it running when you blow them down?
Now, I think that your answer about having pressure to do a good blowdown is good.
Yeah.
I have heard people say that they worry about the magnetite getting blown through when you pull the magnet off if the pump
Yeah.
is running.
Oh, that's a
Instead
good
of the
point.
magnetite falling to the bottom of the barrel, it could then get blown through the body and back into the piping. So
That's an
I guess
excellent
that would
point.
be one argument to turn the
Yeah.
pump off just for a minute.
Yeah, and that would probably be the preferred way now that you explain it that way. In fact, another thing that and we'll do this on another thing. If you're using our quick setters that have this on here, just know that there's a little magnet inside here. And if you pull that ring, which I did twice on this, what'll happen is those little deposits will go in here and they'll get stuck to that magnet. And now your little ball doesn't move anymore. You can replace these. Actually, I can show you hacks someday on how you can take that apart and clean it. But so if you're going to put a lot of metal in a display with a quick setter on it, don't pull the ring when you're trying to demonstrate all the metal going around here. You'll pull it right into your magnet inside. I mean, it's going to go to wherever there's a magnet, and there happens to be a magnet inside those quick setters. So just know that if they stick, that's what's happened. You've got some crud stuck on the magnet there, and you might have to replace that meter, which comes off.
Another question here from Steve. Is there a time limit on how long you leave the valve open when you're doing a blowdown on a smaller residential separator?
Well, we've actually got a really good video of that. That it's a job in, where is that, in Wisconsin? Right on the Illinois-Wisconsin border, I think, of a fellow that put one of those in. It was a big one, a 3 or 4 inch. And every time he blew it down, he took his little camera and did a little video of it. And he sent it to us and showed us. And what you'll see is when you have a lot of that black stuff in there, and you saw it a little bit when I first blew this one down, is you'll see it come out black for a minute. And you want to run that until that water, maybe not clear, but stops running black. Because if it's running black or even gray, you're still flushing those metal particles out. So you might have to run a gallon or two on those bigger separators out of there to make sure everything that's collected in that bottom bowl has gotten good, pressure and good flow around it to actually blow it out. Now, if it doesn't come out, the magnet's going to keep it in there until the next time. But usually you want to, blow them down until you stop seeing stuff coming out of there. The copper you didn't see in there because it's copper colored. But what I did is when I had this, if I've got one here, what I did is when I had it in there, I actually put the magnet on the side of it, and all the stuff that blew out of there, I could actually pull it all together and bring it back to the clump of the stuff I put in there. But obviously the copper and the other particles I put in there didn't stick to the magnet, the sand and the some of the PVC chips and sawdust and stuff that I put in there. But
yeah, that video is available on the Ask Caleffi website. If you go to Caleffi North America on the homepage, there's an Ask Caleffi menu item, and do a search for what does magnetite look like, and you'll see that video that was at a facility in here in Wisconsin.
Yeah, thanks. And so here's what I wanted to show you too. I don't know if I explained it, but when we test this, we could test it at different passages. So we look at the efficiency after 50 trips through the separator, and you can see obviously the further out you go on the smaller particle, it's going to take more trips around it. We get these big particles, like I say, pretty much the first trip around there. If you look at the dirt cal, the green line here, we're up about 100% efficiency on the big chunks right away. These smaller, again, 5 micron, the size of a hair on your head maybe, they do take a few trips around the system to get all those pulled out. So it's not a, one trip around there. It could take, a day if you've got a huge system for all those little particles. So don't, stand there watching and say, okay, I'm going to blow it down before I leave and everything's going to be fine. It's going to take, on a big system, it could take a good day or so for all the fluid in that system to make 50 trips around through that separator and start getting the small particles out. So.
And another question, Steve Martinez says, I'd like to install hydro air seps on all my boiler installs. What are your thoughts?
Yeah, the hydro seps. Yeah, I'm a huge fan of hydro separators. I mean, we've got the SEP 4 that gives you great air elimination because it's got the same media that we talked about here in this week and last week. We've got the good dirt separation, we've got the magnetic band, and it's got the closely spaced tees, basically the 4 ports that make it a separator. So if you look at all 4 functions in one, and you look at the cost of those 4 separate functions, if you're even putting magnetic separators on, I mean, it's a no-brainer. With that being said, not every boiler needs a hydraulic separator. If you're putting cast iron boilers in still, I don't know that you need a hydro separator. It's nice to have all those functions, but really, if you can just flow through that boiler without any flow restrictions, even some of the fire tube boilers are being put in out there that can direct pipe without having to have a primary, secondary hydraulic separator. It never hurts to put one in, but certainly any of the high pressure drop boilers, you want to put a separator over closely spaced tees. And we're going to do a closely spaced tee, primary, secondary. Is that the next one up? I forgot which one it is, and I'll show you, the pros and cons. I'll be fair with you. If there's no need for it, I'm not going to tell you to put one in, but knowing when it makes sense and when it's, going to give you enough advantage to make worth the cost of putting it in, I'll let you know my opinion anyway. So I don't know if it's my boss's opinion, but yeah, so.
Yeah, it's good. Got another question here. We're right in an hour, but if everybody wants to hang on, we'll keep talking.
Sure.
Bill D'Agostino asked, if you were to flush a system, would you get a better flush if you reversed the flow? What I mean is you push through the return and out of the supply.
I don't know about that. I think I'd go in the same direction. The problem with trying to reverse, if you've got check valves and circulators, you might not be able to reverse flow through all those systems, through all the piping and stuff like that. So, yeah, I don't know that there's any advantage to going backwards. Do you have any thoughts on that, Kevin?
I agree with you. I think the flow should go in one direction. You're probably going to have a check somewhere in there, right?
Yeah, well, most of the circulators have them now, or I thought I had a picture here of a purge cart that I could bring up quickly, and maybe I did. It's too far back. Yeah, the use on the separator, the valve's on the bottom of it, and the flow is going to come from wherever the fill valve is attached in the system. If the fill valve happens to be downstream from the system, well, yeah, the flow might be coming backwards from the fill valve to where the separator is. So, usually when we do separators, we have the expansion tank and the fill at the separator, because that's a good point of no pressure change for the whole system. What happened to I was looking for the one with the flush card in it where we had that T. Sorry about all the scrolling. Here it is, right here. So I've had people say when they do something like this that they can reverse the hoses and go 2 different directions. Now, as long as there's no check valves here, you could do that. You could flow this direction through the piping, through the system, and come back out the other one, or you could, switch your hoses and go the other direction. So, if you switch the hoses and nothing comes out, it means, well, the check valve's here and no water's going around and coming back this direction to get back down to the separator, to the purge point. So I guess it would depend on, how the system piped and if there's any check valves in it that could prevent the reverse flow. But you can see what I'm saying here. If I had my, you can see it right here, my fill valve here. So the water is going to come in here and flush it out here. If the fill valve happened to be some other location, if it was over here, obviously I'm going to come backwards through the separator and blow it out, I guess. So.
Yeah, lots of good information here. Howard says, how do I watch this again later?
Yeah, I mean, we're going to have these archived on our YouTube station, as well as Mechanical Hub is archiving all these, the ones that Taco's been doing, on the Taco After Dark. They do theirs on Monday. We're doing ours on Wednesday. So I think all theirs are being archived there. Ours will be archived on the Mechanical Hub, and of course, ours will be on the Caleffi YouTube station also. Caleffi, there's a lot of great videos on the YouTube station. I was watching some today, getting some ideas from Romania. I didn't know what they were saying, but it was just interesting to see how they pipe a boiler differently there, and just to see what the rest of the world does with hydronics. So it's kind of, if you've got a lot of time at home with nothing to do, you can go to the YouTube station and watch a lot of different countries. So, all right, anything else? Or?
Well, that's about it. So Drew says, in terms of the number of blowdowns, so maybe 2 blowdowns. I think we talked about that a little bit. You just keep at first, if you've got an old existing system, right, you want to do it quite a bit. After just a couple of days, maybe 2 or 3 times, and then maybe wait a week. And I think that's what you said last time, right? And just do it a few times until it looks cleaner. You know, you don't want to bring all that much oxygen into your system, but it's kind of a judgment call as to how much crud you're getting out, right?
Well, and yet that would be the catch-22 of it. And anytime you put fresh water, you're putting more minerals in, you're putting more, oxygen in there. So you're kind of, adding to the problem at some point. But yeah, I mean, if it's a really old, dirty system, you might have to go back there for a year and flush it out a couple of times. I mean, the key is going to be if you go back and you just hardly get any out and the water runs clear after just a few seconds, it's probably pretty much done its job unless somebody breaks into it or disturbs some piping and knocks some other stuff loose. So I think every system is going to be different. I do it even on a brand new system. I'd come back probably the next day if it's a heating season and the boiler's been running and all the zones have been open overnight, run for 8 hours or so. If I come back and I just get a little bit of, copper shavings or whatever stuff you put in there when you put it together comes out, that system's probably going to be good to go. Now, if it's an old, iron pipe, cast iron radiator system, yeah, you might have to blow it down every year as it keeps doing its job. It just depends on what the system's comprised of and how much of it's flaking off and stuff. I mean, when I see this black stuff here, I mean, you really need to address why that happened. I mean, I'm going to get it out of there by flushing it like Kevin did in this picture and also by putting my magnetic separator in there. But if this is ongoing, you got an issue there that you got to address. I mean, I'm treating the symptom by pulling this out for you with my separators. The problem is where this is coming from, and it's going to keep doing it. And I would be willing to bet, and I'll ask Kevin when I talk to him, I'd bet $100 that came out of an old non-barrier, radiant tubing system. It could have been rubber, could have been polybutylene, could have been some of the early, PEXs that people put in without putting an oxygen. People still put PEX in without oxygen barrier. That's usually when I see that kind of quantity of that black magnetite. Oxygen's been getting in that system a lot, like every day, and it's just breaking everything down in that system and just turning it into its natural element. The oxides and that are just coming apart basically. And the same thing with this one. I mean, that's just basically rust there. So that's going to take a bit to pull that out.
How does the flush cart filter out the system debris? Mike Morrison asks.
Yeah, so what you can do with this, there's a strainer in the bottom of that. And the way this flushes out is you put the flush in and then the water is coming back here. And basically the strainer keeps it from going back into the system. Now you could put different meshes in there. I don't even know, Kevin, if you know. I would think the mesh that we're putting in there is probably like that. I mean, you could get a finer mesh to pull some of this stuff out, but yeah, you've got to catch it in this tank here and then obviously flush the tank out. So, I mean, this usually here, if you're flushing out an old system, you might want to just take this return hose off of the cart here and just blow it out in the driveway or floor drain. Or I like to do what Kevin here is doing and blow it into a bucket so I can see what's coming out of there. I want to know what that stuff is. So I would take this hose right here. No, that's actually the discharge hose. This hose here, we actually put a connection on it now that you can connect that to. I would take this here and just put it into a bucket or into something that I can capture what's coming out. And then when I see it start to run clean, I'll know it's time to put the system back together and let the separator do the rest of the work. But this is just going to do the heavy lifting for you on a dirty system like this. And also it's going to get your velocity up a lot higher than you can get up to with these circulator pumps. If these are sized properly, I'm going to be running up around that 4, maybe 5 feet per second when these are running at the, their designed capacity, their designed flow rate for that loop. So I don't have the ability to flush a lot of dirt and debris out unless I get a lot more, flow velocity. So 5 feet per second is what I learned from the people that do this for a living, is what it takes to get a particle moving through the fluid. In fact, I was going to put a video in here that PurgeRite, the company out in Texas that does purging, they've got a nice video on their website actually. If you go to PurgeRite.com, it's a company in Willis, Texas that goes around purging out big systems. They'll purge out a 24-inch diameter pipe if you need them to. And they've got a video on their website and they show the velocity feet per second that it takes to move something. And they've got a big bolt, like a 1/2-inch bolt and a nut in there, and they put it in a clear plastic pipe, and then they keep increasing the velocity in that pipe. And you'll see it gets to a point where that bolt just starts moving right up out of the top of the tube, or that nut, that 1/2-inch nut they had in there. You'll see it kind of hovers in there, and all of a sudden he said, watch this when we get up to 5 feet per second, or what it shows on the video as they're doing is what it is. And you'll see that nut just goes right out the top of the tube, and that's what it takes. You got to get that flow velocity up if you're going to get big heavy particles of metal or rust or whatever's in your system. That's the key numbers. That 5 feet per second velocity is when things start to start to move around on you.
Well, it looks like we've answered pretty much all the questions, Bob. If there are some more, we will type up answers and get them back to you.
Yeah.
Going through those now. Mary or Mark or anybody else have any comments or questions before we let Bob go?
Well, I think the most important thing is that we hope you can join us next week, but you do have to register. So, check out our webpage. We will send out an invitation too, but we'd love to have you back. Bob will be talking primary, secondary education. Yep. Okay.
Yeah, some tricks that you might not have known about primary, secondary, I'm going to share that I've learned, number one, and that Siggy's taught me and some of the other people out there. So yeah, thanks for my support team, Mary and Kevin and Ellen, my wife here, and everybody else that helped me put this together. And
there's Ellen. And please be generous for the Red Cross.
Yeah, please donate, and then we'll donate too, and we'll keep doing that for everybody in these days. So thanks everybody for your time and hanging in there with us and sending questions for the next one, and call me, text me, however you want to communicate. I'd be glad to chat with you and help you. I'm sitting home too, so I got time on my hand these days. So,
thanks very much, Bob.
Thanks everybody.
Thank you.
Bye-bye.
Bye everyone.